Hi everyone, I'm going to be going over question number 21 from the Chapter 8 Bingo Problems. Now, I'll start out by reading the problem. It says, on a frictionless horizontal air table, puck A with mass 0.25 kilograms is moving towards puck B with mass 0.350 kilograms, which is initially at rest. After the collision, puck A has a velocity of 0.120 meters per second to the left, and puck B has a velocity of 0.650 meters per second to the right. And then part A says, what was the speed of puck A before the collision? And then B says, calculate the change in the total kinetic energy of the system that occurs during the collision. So I've already organized everything by puck A and puck B. I figured that would be the easiest way to keep the information organized. And so it wants to know the way I've notated this, the initial velocity of puck A. So to start out, we know that momentum is going to be conserved. So we know that the initial momentum is going to equal the final momentum. And so if we break this up, we know that the final momentum, or we'll split these up. So we'll say the initial momentum equals the final momentum, which is going to be V1F plus or actually we'll do it initial first with puck, or with the initial. So we'll keep the initials together, and then the final momentum is going to be M1 V1F plus M2 V2F. So this just expands, what we already know about momentum, because we know that momentum equals mass times velocity. So now that we have these, what we can do is we can set them equal to each other, right? Because we know the Pi equals Pf. So then we'll get so we get M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. But now what we can do is we're looking for the initial velocity of, really this is like 1, and this is 2, the way I've notated it here. So really what we're looking for is this right here, the initial velocity of 1. And so the way we do that is we just isolate it, simple algebra. So we'll end up with V1I equals M1 V1F plus M2 V2F minus M2 V2I, right? So subtract this over and then divide both sides by M1. Now what we can do is we can just plug in the values that we already know. And so we end up with V1I is equal to 0.25, the mass of puck A, times its final velocity, which we know is 0.12, but since it's to the left, we know it needs to be negative. Since, at least in the reference frame that I like to use, left is negative, right is positive. So we'll do that, plus, you know that M2 I got confused looking at my notes. So we know that the initial velocity of puck B is 0, right? So we know that this whole part is just 0. And so then what we end up with is plus mass 2, which is 0.35, times the final velocity, which is 0.65 meters per second, to the right, so it's going to be positive, and then all this is over 0.25. Now we just plug that into our calculator and we end up with V1I, actually I'll just put it right here since we already have a spot for it, is equal to 0.79 meters per second. So that's it for part A. So we found the initial velocity of puck A before that collision. So now that we've figured that out, now part B wants to know the change in total kinetic energy of the system that occurs during the collision. So to do that, we know we basically do the same thing that we did in part A, but instead of momentum, we use kinetic energy. So we know that the initial kinetic energy equals 1/2 m1v1 I squared plus 1/2 m2v2I squared, and the final kinetic energy is 1/2 m1v1 final squared plus 1/2 m2v2 final squared. So now that we have these written out, we can well, first of all, we can kind of condense it a little bit, get it a little bit easier to work with. So like the initial, we can pull out half, and so we end up getting Ki equals 1/2 m1v1I squared plus m2v2I squared. And then the same thing for final, so Kf equals 1/2 m1v1f So you don't have to do that right here, but I know like the less I have to write, the less chance I have of screwing it up. So I like to do it right here. So we have that, but now we also know that the change in kinetic energy is equal to Kf minus Ki. And so to find delta K, which is what part B wants, we just subtract. So we know, so delta K equals 1/2 times m1v1f squared m2v2f squared minus 1/2 m1v1 initial squared plus m2v2 initial squared. And so I know if I kept these halves in here and didn't, FOIL it out, or however you want to say it, bring it out of the equation, I know I would mess all of this addition and subtraction up. So I'm glad I did that. So now we have it all figured out. Now what we need to do is just plug everything in and solve for delta K. So we know, so delta K equals 1/2 times 0.25 times the final velocity of 1, which is a, so 0.12 squared plus the mass of b, which is 0.35, times the final velocity, which is 0.65 of b squared, minus, use another row because this is really long, the square root of m1, so once again 0.25, times v1 initial, which we found out in part A, which is 0.79 squared, plus 0.35, and then our initial, which is just 0, squared. So this all is 0, which is nice. I'll just erase it, and then we plug everything in. So when we plug all this in to our calculator, we end up getting that delta K is equal to negative 0.0023 joules. So that means that the whole change of energy with this collision, I mean, it's not really that exciting of a collision, right? It's just these two objects that kind of bump into each other. The change in kinetic energy is pretty dang small, but energy is lost, and so that's going to be, put into probably thermal energy, since we know that it's like a frictionless horizontal table. So my guess is that that would all basically be thermal energy, maybe some other stuff in there as well. But anyway, so to kind of do an overview, we were able to find the initial velocity of puck A using the conservation of momentum. And then with B, we were able to use what we know about kinetic energy to find the change in energy from the before the collision and after the collision. So anyway, hope you enjoyed watching. Hope you learned something. I'll see you in the next video. Thanks for watching.